last times we discussed a little bit the qualitative behavior of initial boundary value problems as we are encountered with in conjunction now with the time-dependent version of the stationary elliptic problems we dealt with up till now. And I indicated already that it is advisable to treat the time, and that we also have seen in terms of the explicit solutions and the qualitative behavior of the solution, it's advisable to treat the time different than the spatial coordinates, and not to say, okay, we have a problem in d+1 and we apply finite elements in d+1, or just finite difference methods, which could also be possible. So doing so, it is also of advantage first to think of an intermediate step, which is not fully practical in the sense that it's not fully, what comes out is not fully computable, but the intermediate step in terms of semi-discretization. And there are two possible versions of semi-discretization, the horizontal one, the Rothes method, and the vertical one. In the horizontal one, which we are not dealing with here, one first discretizes in time but gets a sequence of connected elliptic boundary value problems which we know how to treat. Here we do it the other way around. We discretize in space first in the way we developed it. So at the moment we can do it either with a finite difference method or with a finite element method. And we'll see there's a strong parallelism between these two methods. So because in both cases, and in principle in more or less all the cases, one treats the time derivative by finite differences. We have a very simple domain for the time in terms of an interval compared to the, in general, very complicated spatial domain. So if you later on will know more ways to discretize, for example, finite volume method, mixed finite elements, DG, or whatsoever, the development is very much the same. So we start with the most simple situation we know, namely the finite difference method, and here with our, to be specific, with our model problem, that is with the heat equation. So all coefficients in the equations are scaled to 1 with Dirichlet boundary conditions, and we take a rectangle such that we can apply finite differences without any problem. And we know what comes out, namely the 5-point stencil in the stationary case, and exactly the same procedure we now do in the time-dependent case. So we have, let's think of a smooth classical solution. We fix an instant of time. We keep the time derivative as it is, and we perform the spatial derivative in the way we started with. So we get here the 5-point stencil in the natural double index notation here, and correspondingly the right-hand side evaluated, now also depending on time, and correspondingly the boundary condition with the right, with an heterogeneity which now also might depend on time. So what we got here in this procedure, and this will be maybe a little bit clearer if we write this again in matrix notation. In the stationary problem, we got we got a linear set of equations for a tuple, for a grid function. Now we have a system of ordinary differential equations. System in that is the solution is a tuple or the solution is a grid function. Depends how we would like to see that. Whether we fix an ordering on the grid points or not. Okay, so without the time derivative, we always written this problem as AH times vector tuple vector u equals a right-hand side, and now we do the same thing. Now the solution becomes time-dependent, the matrix not, because we have assumed that our coefficients, which are in this case, okay, constant equal to 1, do not depend on time. But you see, in some sense, one could do basically the same thing if we would have general coefficients, and even if we would have time-dependent coefficients. Then we would get here a time-dependent matrix. Now we have just a constant matrix in time. So here again, the abbreviations which I use. So this is now as up till now in the finite difference context, just the evaluation of the right-hand side and of the heterogeneity of the boundary conditions at the grid points. But now that is now the difference also t-dependent. So we get now not a vector, but a function in t with images being a vector of being grid functions. And correspondingly, we need our initial data. Fragen Sie ruhig. Okay. Correspondingly, we have our initial data, and again, we approximate the initial data by evaluating the function. Of course, this requires enough smoothness for the initial data, and we could think also of something different here. Evaluate the initial data at the grid points. Good. Ist das ein Okay. So now let's write this analogously in our matrix notation. And the matrix AH is exactly the matrix AH we had before. It's exactly the matrix if we do, for example, the row-wise ordering with the 4s on the diagonal, the minus ones at the upper and lower diagonal, and then as many points as we have in the vertical directions away, another minus 1. So this is block tri-diagonal, basically this block tri-diagonal matrix here, or a permutation of it. And the difference now is our problem now does not read AH, UH equals QH, but it's now this system of ordinary differential equations. And as we started with a linear problem, and as we did discretizations which preserved linearity, which seems quite reasonable. Actually, more modern methods do not do that. There are also nonlinear approximations for linear problems. If one wants to have more conditions to be fulfilled as one can do with linear approaches, but in any case, here we have a linear approach, so we get a matrix here, we get a linear mapping. So this is a linear system of ordinary differential equations. Okay, so and that is the function we are looking for. So the image as one instance of time is a tuple in Rm1, M1 being the amount of unknowns in the non-Dirichlet, or here in this case in the interior boundary, in interior points, or is a corresponding grid function, and that is the corresponding stationary problem with which we have dealt up till now. So now it depends how much you know about ordinary differential equations. Who had a course on ordinary differential equations? Okay. We do not need too much. In principle, this should be basically more or less already known from analysis. So first of all, ordinary differential equations, contrary to partial differential equations, are ordinary. In the sense there is at least a part of a unified theory, which maybe doesn't say too much, but there is one. And for PDEs, every PDE is sort of an individual, at least the different classes are. So the first question, of course, is what about existence and uniqueness of a solution? And here you might, if you had a course in ODEs or if you are in engineering mathematics, then you should have heard this, that there are basically two important theorems, and the more specific one is the theorem of Picard-Lindelöf, which tells us that such an initial value problem for a system of ODEs has a unique solution, local in time, if the right-hand side is locally Lipschitz in the variable UH. As it is, so for this consideration, we have to put, so to speak, this part to the right-hand side. This gives us our right-hand side, which usually is then called f of u and t. And of course, this is even globally Lipschitz because it's linear here. And due to the linearity, we could also then ensure that the solution is not only local in time, but it's global in time. So concerning existence and uniqueness, there's no problem whatsoever with this problem which we have here. It would also be true if the AH would depend in a reasonable way on time. So if we would have started with an equation which has, so to speak, full set of coefficients which would be also allowed to depend on time, which we have excluded at the moment, or we have excluded to make things more presentable. There's a further advantage in this time-independent version here for the coefficient matrix is that if we know a little bit more about this matrix AH, that we have actually a representation of solutions. And even if you had not had a course in ODEs, at least I would hope you have heard about this in the linear algebra, because it's a very good application of eigenvalues and eigenfunctions. If the matrix A is diagonizable, if we have a basis of eigenvectors and corresponding eigenvalues, then we can represent the solution in terms of this basis. And the exponential, we will see this later on, we will do this later on. We remember the solution representation we got for the continuous problem in the special case of interval or a rectangle, or a situation where we could compute exactly the eigenfunctions for the underlying elliptic boundary value problems. And there we have seen the same structure, basically a solution built up of summands where one constituent was the eigenfunction and the other was an exponential term with the eigenvalue. Or better to say with minus the eigenvalue, minus eigenvalue times t. So in case of positive eigenvalues of we get strongly damped components. In case of negative eigenvalues, we would get exploding components of the solution. And this representation of the solution we will use later on too as a start. Okay. Now let's do the same thing for the finite element method. And here we don't have to do any restrictions. So we can allow for all kinds of boundary conditions. That means we get corresponding boundary integrals in the right-hand side if we have heterogeneous Neumann or flux or mixed boundary conditions. And we do the same idea. So we take our variational formulation, which we have put down as a Week's notion of solution for the time-dependent problem. Maybe I remind you how it was. So let's first forget about all the h's. So we've put down basically this formulation for as a notion of weak solution for the continuous problem, of course, for all v of vh. And we are looking for a solution u from L2 0 t v such that this term makes some sense. So we had to introduce a corresponding weak derivative, and in this sense the derivative was required to be an L2 function in time with values, but now with values only in H. Of course, being in this infinite dimensional spaces, this makes quite a difference whether we are in V, we are in H1 omega, or we are in H in L2, in the much bigger space. In the discrete setting, there is sort of these things then come together. And now we do the same way, we do the discretization the same way as we did it before. We do, so to speak, also the Galerkin-Ansatz. That means we are looking now for a solution which takes is for each instant in time in the discrete space VH. So for each instant in time we get, so to speak, a finite element function. And we require that this variational equality is now only satisfied because we now have only, for fixed instance of time, we only have a finite amount of degrees of freedom. So we can only pose a finite amount of requirements, and we now only require that the test function is from the corresponding ansatz space, or is the ansatz space. It's exactly the same thing as before. The only difference that we have now this time derivative here. So now if we now work out what this means exactly in the same way as we did it, so what can we do? First of all, what we know, what we have mentioned last time, these requirements here mean that our function is a continuous function with values in H. That also means that the initial requirement, so we also have to specify, of course, here an approximation for the initial data, that the initial requirement makes sense because now the solution is continuous in time, at least for values in H. And so we can fix an instance of t and do exactly what we did before. That means we represent the unknown solution as a linear combination of the nodal of a basis function, any basis function. Think of the nodal basis functions. The only difference is now that this psi vector now is dependent on t. So it's not just a vector, it's again now a function from the interval to the tuples, to the grid. Or you can also call it here grid functions. Maybe it's not so convenient here. Okay, so what happens if we, that we plug in here and here, of course, and in the same and similarly the requirement which we have here for the full finite dimensional space is equivalent that it's valid for the basis. So we plug in the basis here. And that was the reason that if we only look at our old parts, this part and this part, for fixed t, say, we get a, forget about this term for a second, we get again our set of equations with the stiffness matrix of the load vector. Now, at least here the load vector t-dependent. And for the stiffness matrix, the same remark applies if we would have coefficients which in their whole formulation would be time dependent, we would get the same thing, but now also time dependent here. So we have these two terms back. And now what happens with the first term? In the first term, we have no spatial derivatives. It's just the L2 scalar product. So first we have the time derivative of UH. So the time derivative of UH, because Vi is t independent, is only spatial ansatz functions. We don't have a space-time ansatz. This time derivative just goes through to the sum to the xi's. So here we get the time derivatives of the xj's as the coefficients. And now if we multiply out, we get again here a matrix of this type as here, but now not with the A scalar product, but with the L2 scalar product. So you see now here the matrix appeared, which we have discussed already, namely the mass matrix. This is the mass matrix. So this is just integral over phi j, phi I, what stands here. And we discussed the mass matrix already in conjunction with estimating the condition number of the stiffness matrix. And here you see how the mass matrix appears naturally in the discretization of time-dependent problems. So, what is the difference to the situation we had before? Of course, this here is now much more general, but the overall structure of the problem is exactly the same. Again, we have now a linear system of ordinary differential equations. Now for the psi-i's, which have, of course have the advantage that they have a clear interpretation, namely they are the nodal values for each instant of time of a solution, which has then some regularity in time, and in space it's an element of VH. That is the difference between a finite difference ansatz, where we only get grid functions, and a finite element ansatz. So if we now summarize the right-hand side now with beta h, okay, we could have also done QH, doesn't matter. Not sure why I took here another letter, but I hope it's not so much of a problem. We have here an AH, which are now called AH hat for some reason, which is just here the old stiffness matrix. And here again, here that's the new part. Here we have the mass matrix, as I said. The mass matrix is a nice matrix in the sense, of course, it's symmetric, and it's also positive definite, because if I plug in, look at the quadratic form with a vector psi and a vector psi, I just get the L2 norm squared for the corresponding function. So this is not really an implicit. It looks a little bit as it would be an implicit. I do not really dare to use this notion. An implicit ordinary differential equation. In fact, it is not, because really, this B what you can do. The most simple version would be to multiply with the inverse of B. Then you get the classical form, the canonical form of an ordinary differential equation back. That would be not so good, because if we would have, for example, here also symmetry and positive definiteness and things like that, that would be destroyed by that. So actually, if one would really get rid of this BH, one should do it another way, namely, the BH is, as I said, symmetric and positive definite, so it has a Cholesky decomposition in this sense. So we can decompose this matrix in a matrix transpose times a matrix. Cholesky means that can even be done in the way that this matrix E is an upper triangular matrix. That's not really necessary. We need only any of such a decomposition. And having such a decomposition, then we can first of all transform the variables. So now instead of xi, we use EH xi h. And so we incorporate the half, so to speak, of the BH in the unknown. To have now the right unknown here, the EH to the -1 has to appear. And now we multiply again with the EH to the -t, and then we get here a new matrix, which is a congruence transformation. Where is it? Oops, where is it? Here it is, which is a congruence transformation. So I have a non-singular matrix, and here I have the transpose of the non-singular matrix. So any properties which this matrix here has, so with the matrix AH hat has in conjunction with, say, quadratic forms like symmetry, positive definiteness, and so on, everything this is conserved by this. In this sense, that would be more reasonable to do it like that. Actually, this is only to assure us that that's really the same two systems we are dealing with. For in the numerical situation, we would not do that. We would just keep the B where it is and work explicitly with this matrix B. We will see that if we then also will do time discretization, what I mean with that. Okay, maybe another remark. We'll come to this later on. Yeah, maybe I ask you, is this good or is this not? So this matrix BH. So we have the matrix BH there in the finite element case, and in the finite difference case, we have just the identity matrix. Or if we would have coefficients there, we would have just a diagonal matrix. The matrix BH is also a sparsely populated matrix, but in general it's not diagonal. Is this good or not good that this is not a good this is not a diagonal matrix? We'll later see. Yeah, okay. What is your opinion? Should it be a diagonal matrix or doesn't it matter? Or it seems okay because it comes out of the finite element method? Do you have any feeling for that? Now, totally independent of algorithmic problems we might have with that, just in terms of the quality of solution which comes out. What does this time derivative term represent? It's a storage term. And it's a local term. In the way we formulate it, the PDE, or before the conservation law, there's no interaction with neighboring points. But what does now this non-diagonal mass matrix do? What does it mean? There's a sort of a smearing. It brings in an interaction with neighboring points for this term, which qualitatively, if I fix my discretization, I look at my discrete solution, what it does, how it looks like, where it comes from, it's not okay. That's a failure in the qualitative behavior of the solution. The matter is how serious this is, because later on we will see all our methods are converging. So we can rely just on the convergence or order of convergence of this method and say, okay, there might be something not okay, but asymptotically this goes away. But that's what is one point of view, and another point of view is to say no. The only thing what we are doing is we are computing discrete solutions for fixed discretizations, and we want to have that also these discrete solutions have the right qualitative properties, that we have more confidence in them. And that would mean one has to do something to, that means one has to substitute this matrix BH by a diagonal matrix. We will later see this is easily to be done if we just approximate the matrix by quadrature. So we substitute the exact integrals, which are only, in this case where we have only coefficient 1 in front of the time derivative, but usually you would have their coefficient function space dependent, so you would not be able to compute the mass matrix at all, in principle. And if we do then quadrature approximation by nodal-based quadrature, then automatically this matrix becomes diagonal. But of course we have introduced an additional error by this quadrature. So you see there's always a little bit of a conflict of accuracy and qualitative behavior and maybe also stability here. Okay, so finite volume we do not know already. So let's go. But this is also very similar. So let's now go back to the finite difference case. This is still finite volume, I think. To the finite difference case, and let's see what we can do. it will not be too much and it will not be rigorous, because, as you will see, but it will give us a little bit of an indication what can come out. So we go back. We go back to the specific situation where we can, let's say the specific situation of the heat equation on the rectangle, where on the continuous level we can write down all the eigenfunctions, know the eigenvalues, and the approach now is so to speak, a pre-computer approach. We also try to write down closed form solutions now for our discretization and see how they relate to each other. It's very much restricted because we have to know the eigenfunctions and the eigenvalues to do things like that. So how is this on the discrete level? So if we now are in a situation, it's a little bit more general to what I just said. So what we have this matrix AH, and we have to have a basis of eigenvectors, which are called here Wi, and corresponding eigenvalues lambda I, which here are supposed to be real. I'm not so really sure whether we need this, but as we know, we have a continuous problem which has real eigenvalues, which has even in general positive or non-negative eigenvalues. It would be a little bit strange to have here non-real eigenvalues. What would that mean for the solution? Let's assume on the discrete level, on the spatially discrete level, we would have a real complex eigenvalue. What would that mean for the solution representation? You remember from the ODE situation. Okay, so we answer this question then in a second. So what can we do? Of course, we can represent the initial data in an exact manner, in a unique manner in terms of these basis functions. We can represent the right-hand side correspondingly. Now the coefficients become time dependent. And we get now a solution representation which is very analogous to the separation of variables solution. Namely, we get this solution, which I really would hope that you have seen this already. So we have a solution part which reflects here the initial data. Here the CIs come up. So this part is sum over the CIs. Now here comes the, let's say, damping part, damping for positive lambdas, E minus lambda IT times omega I. So it's just the same solution coefficients, but now correspondingly damped. And this is the part that is, so to speak, the variations of constants formula part for the right-hand side, which takes those now time-dependent coefficient functions. There is a weighting term in time, which means that all the past enters. We have not only the value at t enters, but all the past back to t0 enters, but the weighting function diminishes the influence of that quite dramatically going back. So that is very similar to the formula we have seen already. And now let's write this a little bit in a more compact fashion. And okay, now I ask you again. Let's make it simple. Let's only look at the influence of the initial data. In the situation where we have positive eigenvalue, where we have real eigenvalues. So this means all the eigenvalues are positive or non-negative. Then we have decaying components or one persisting, one constant component. If we would have negative eigenvalues, that would mean we would have an exploding component. What would that mean if we would have non-real eigenvalues? Oscillating, yes. Because then we have here the complex eigenfunction, we have the real part, which behaves exactly like this here. And then we get, in addition, the imaginary part, which brings in a rotation, or is a rotational part. So this is an overlay, then if you write it in a real format of E minus real part of lambda IT times cosine imaginary part, and so on. So it's the same type of solutions, but they start oscillating. Okay, maybe we do not like to have oscillating components here in this case. So in any case, therefore, we now have assumed that we have at least real eigen values. Now the next step, which I also would hope you have seen already, we can write this version here in a compact fashion, namely like that here. For that reason, we have to define the matrix exponential. Who does not know the matrix exponential? Okay, that's good. Maybe I should have asked the other way around. So this is the question. I have a function, a function on the reals or on the complex numbers. Can I also define this function for a matrix, or under which circumstances I can define this function for a matrix? And this can be answered in different generality, this question. And what comes out in general is that the exponential function can define for any matrix, for any quadratic matrix, of course. Why is this? We could either say this is sort of a more restrictive approach. Would say, okay, I only look for functions which have a power series expansion. And then I asked myself, if I now substitute here the real or complex argument in this power series by a matrix and do formally exactly the same thing. Now, of course, here in matrix space, and we know in matrix space all norms are equivalent, we just have to take one. In which cases do I have convergence here? And the answer is I have convergence as long as the spectral radius of the matrix is below the radius of convergence of the power series. And as here, for the complex function, the radius of convergence is infinity, we have no restrictions whatsoever. Of course, now we have to see how does this relate to the eigenvalues. And why is this term, for example, maybe we only look at the first term, why is this term, so the sum ci e to the minus lambda t times wi, nothing but what is here written a little bit more compactly with e to the minus aht u0. Maybe this is a little bit confusing here. What does this mean, ah times t? This, of course, means t times ah, the scalar t times the matrix AH. But to be a little bit more suggestive, more in the direction of this notation, I now from time to time write the scalar parameter, the scalar factor behind the matrix. Okay, let's do the computations why this is the case. So we take our basis of eigenfunctions and plug the columns one to each other, so we get the matrix T. We take the eigenvalues and form the diagonal matrix lambda. Then having this eigenfunction eigenvector eigenvalue relation just means AH times T equals T times lambda. If you write this down, what does this mean? Matrix times matrix are columns which are matrix times the corresponding columns, and then you are back to the AH omega I equals lambda I omega I version. So, or otherwise written, this is this statement. So the similarity transformation induced by T just leads us to the diagonal matrix. This is just this tautology. saying what does it mean a matrix is diagonalizable? That is nothing but saying there is a similarity transformation to a diagonal matrix here, and again by this it's nothing but saying there's a basis of eigenfunctions, eigenvectors, and these eigenvectors produce the transformation matrix. Okay, now we do this. We do the same similarity transformation we start, so to speak, from the back, on the matrix exponential. What does that mean? We can plug so this operation of a similarity transformation is a continuous operator on the space of matrices, so we can bring this through the limit, so we can multiply this in here, not only in the partial sum, but also bring this multiplication through the limit. And now we have the similarity transformation of a power of a matrix, which is the similarity transformation of the matrix to the power. Here this is a line which reminds you that this is true, but the similarity transformation of the AH, of the minus AH, was minus the diagonal matrix. So we only have to transform the powers of the diagonal matrix, which is of course a diagonal matrix with the corresponding powers on the diagonal. And now everything has reduced here to computation with diagonal matrices and also all the convergence business. So in the end we get a diagonal matrix here with has as diagonal entries these corresponding series here, which are nothing but then e to the minus lambda t. And that was so this similarity transformation is not only compatible with a power and not only compatible with a polynomial, which you hopefully know from linear algebra, it's also compatible with such a matrix function. And as you see, one could also start from this part and could say, as long as this function f, which I would like to define what f of a is defined on the eigenvalues of the matrix, I can define what f of a is. Namely, I just take this as a definition in the general case here. But this is only a side remark. So now, in this new notation, what was this? The c, i's, and correspondingly they are put together to a vector c. And this vector c is the coefficient vector for the eigenvectors to form the vector u0. Now, a new notation, this is just this situation. Tc equals u0. And now, look again here what that means. We only look at the first part of the solution, at the dealing with the initial data. So we set QH to 0 to simplify a little bit the computation. The rest is similar. So how does the solution look like? So we have the diagonal. We have the diagonal matrix times. So what do we have? We have here. Maybe we go back. Let's see it again. Oops, where is the solution? It's here. So we have u0 to be still one up. This is what we want to see. Here it is. So we have a linear combination out of the t's formed with coefficients. Here we are, formed with coefficients ci times e to the minus lambda t. So we have t. So where we start off, we have t times the coefficient vector, and the coefficient vector is the diagonal matrix times c. So t times the diagonal matrix we can write as t times the diagonal matrix we are allowed to write then a little bit confused. Now let's do it the other way around. Oops. Looks a bit strange what is here. D times the diagonal matrix is A times T. Why don't it? Like upstairs? We will later on. We want to use this one. So if we have this would be okay if we have this. Then this is U0. This goes away. And why is this the case? Yeah, okay. It's what we have proven is that this diagonal matrix is we don't have to use again because we did this already. We don't have to use the eigenvector property. So we have proved already that this matrix is the similarity transformation of this matrix here. So we plug this in. This goes away. This is our initial data, so we get this compact form. Which, of course, is only a compact form, because if you now ask yourself, now, how do I compute this? The only way we can do so is, again, go back to the eigenvalues. It's only a compact notation if you want, but it helps us to see more the relationship between the different components in the different solution representation, to see what now has happened due to the spatial discretization. Okay. Now we go on a little bit in our requirements, namely we would like to have that this eigen. So this what we did up to now we can do with any eigenvector basis. Now we restrict ourselves a little bit more in the sense that we want to have an orthogonal eigenvector basis or orthonormal eigenvector basis, and this is for sure if the matrix is self-adjoint. You know, the characterization for the existence of an orthonormal eigenvector basis is the normality of the matrix, and so this is the biggest or typical class of that. Biggest, I'm not sure. There are other examples like orthogonal matrices, but self-adjoint is also a possibility. And self-adjoint has a clear meaning for us. It means we only look at diffusive problems. Okay, here there's again a direct proof, but I would hope you remember this. There's a direct proof that in a self-adjoint case, really the eigenvectors for different eigenvalues are orthogonal. And the eigenvectors for the same eigenvalue, so from the same eigenspace, of course, by the Schmidt orthonormalization procedure, we can always choose an orthonormal basis. So in the end, we have an orthonormal basis of eigenvectors. You see this is a one-line proof why in the self-adjoint case the eigenvectors must be orthonormal. We start with this situation here. We get the lambda I in here, so this is AWI. We get the A to the other side. This is the self-adjointness. Again, the eigenvalue property, lambda I equals lambda J. So this term must be 0. So in this case, we know explicitly what the coefficients are. Namely, they are the Fourier coefficients, and that means they have this form. They are just the scalar products of the function to be represented with a basis function, and in case where we have a non-normalized basis, we still have to divide here by the Euclidean, by the induced norm square. So this knowledge we would like now to use to compare in the very specific case of the heat equation on the rectangle the two solution representations. So what are the two solution representations we have? For this reason, we need a corresponding Euclidean norm or discrete norm, and we use the norm with which we started. Now d equals to 2, this correspondingly scaled Euclidean norm, which reminds us that we have approximated here the continuous L2 scalar product, say, by a quadrature rule. So what are now, this is now the corresponding norm. And now of course we need to have for our matrix we need to know the eigenvectors and the eigenvalues. And we have used these so they can be given explicitly. Of course, if you once have them, it's easy to check that they are. You just plug it in and see that it works. And here they are. And we have used them already to estimate the condition number and of the matrix and to see how the different iterative methods which we had converge for this specific example. So what do we have? What do we see here? Let's first start with the eigenvectors. The eigenvectors now should be even more familiar now, because what they are just sine times sine functions. So they are composed out of the one-dimensional situation, correspondingly as in the continuous case, as we have discussed. And if you look closely, you see they're exactly the eigenfunctions of the continuous case evaluated at the grid points. There's no further error, no further deviation. It's just exactly the same functions evaluated at the grid points. Okay, but now of course, as our dimension is L minus 1 times M minus 1, of course, this is exactly also the amount of eigenfunctions which we have here in a basis. It's not infinitely many as in the continuous case. What has happened to the other ones? In the continuous case, we had the same thing here, now not restricted to the grid points, but on the whole rectangle, but the indices were unbounded here. What has now happened to the sine times sine functions with the higher frequencies which are not here? Or why are they not here? Okay, let's draw a picture. I do it only in 1D. Okay, this is my domain omega. And then this is my first, we're speaking about Dirichlet data. This is, so to speak, my first eigenfunction for the lowest positive eigenvalue, the lowest frequent eigenfunction. The next one would be this one. The next one would be this one. Oops. Should be, of course, the same height. Would be this one. Why does it stop at some time? For example, let's say we only have these discretization points. What does this mean for this? This one not. What does this mean, for example, for this eigenfunction here? This continuous eigenfunctions evaluated at these three discretization points. What is it? 0. We cannot see this high frequency function. We can only see what is non-zero at the grid points. But we only have finitely many grid points. And at some place, this is you see the point? They are not gone. Of course, we could answer formally. Of course, we cannot have more eigenvectors here because that's just the dimension of the problem. But that is what we have here. These higher frequencies we cannot see at the grid. Okay, these are the eigenvalues here. They are different from the eigenvalues of the continuous problem. And correspondingly, This is a reformulation of the eigenvalue formula here. And this is these trigonometric identities here behind. I think I'm going now not to prove this identity. I would think you can do this. And if you do this, we get this alternative form here for the eigenvalues. And we will now use always this natural double index notation. So, okay, let's see. Okay, now let's start with this formula here. And what do I do is I subdivide here in the square by the argument. And of course, this I have to correct. So the h square I had already. And I have to correct, so I get here this factor in addition. And I do the same thing with the second term. So my claim is that this first term here in the square converges to cosine of 0. Why is this? Yeah, it's possible, it's possible. Yeah, it's just a difference quotient. Sine of 0 is 0. So there's sine of a, or call it whatever you would like to call this, x minus sine of 0 divided by x. So this is just the difference quotient. Of course, it converges to cosine of 0, that is to 1. So this is good because these are now the eigenvalues of the continuous problem. So the eigenfunctions are the same up to the ones we cannot represent at the grid points, and the eigenvectors, eigenfunctions, and the eigenvalues, they converge. But we do not want to have just convergence. We want to have order of convergence. And my next claim is that the order of convergence which we see here is of the order h square. This would be good because that is actually what we would see in the end. We do a spatial discretization of the order h square, and of course we would like to see that it's all preserved in the time-dependent situation. Why is this convergence of the order h square? Why is this of order h? Maybe we start with this.
We get the finite difference for the taking cost.
This is not sufficient. If the function is only differentiable, just differentiable, then by definition the finite difference quotient converges. But we don't know anything about the convergence. To quantify the convergence, and now you not maybe L'Hopital, but something in this direction, we have to know more about the derivatives. What would be the situation if we would know that the derivative is bounded or is a continuous function? Make it easy. Which could we then argue that there is an order of h? What about Taylor's expansion? Then Taylor's expansion, if we could do this, or we could also do it without Taylor's expansion, we see that there is a term constant times h plus maybe higher order terms. But we would like to have not order of h, we would like to have order of h squared. What is the reason for that? What is the first derivative of the cosine function? At 0. Is it bounded? Is it continuous? It's even maybe more. I would say the derivative of the cosine is minus sine, as far as I remember. And what is this at 0? It's not only bounded, it is 0. there's no linear term in, and it starts with h squared. And that is good. It's very good, because then we see here the h square convergence, which we would like to see. Okay, so the next thing is we have to compute those scalar products of those vectors. That also has to do with trigonometry. That is the number which comes out. And now we have our solution representation. Oops. Maybe did I skip it, or where is it? Or maybe I go down and we first look at the solution representation. Where is it? Here it is. Here it is. So what do we have? We have here our eigenfunctions or our eigentuples. Here is the corresponding decreasing term with the eigenvalues. Here we have the corresponding Fourier coefficients. And what are the Fourier coefficients? The Fourier coefficients are the scalar product of the function to be represented and the corresponding eigentuple, eigenvector. So this is the scalar product from here to here. This is the scaling factor as we just have computed it. And this is the formula for the eigenvalues. So this is the solution representation in the spatially discrete case. Now this we have to compare with the corresponding continuous situation. This is the continuous situation. This is the continuous situation. Now we have infinitely many eigenvalues. The eigenfunctions are the same, but much, much more. The eigenvalues are different. And of course, also the Fourier coefficients are different because we have a different scalar product here. So if you now would like to compare these two solutions, and what does that mean? We have now different parts here. If we now so the first thing is, unfortunately I don't get it on one page. The first thing we have, so what do we have? We have the lower frequency parts which appear here, which they have to compare with each other. Here we have taken into account that we have deviation in the eigenvalues and in the Fourier coefficients. That is one thing. And the other thing is that we have the higher frequency part, which we don't have here, but in the continuous solution. This also has to be estimated. So let's start with this one. So that would mean we have to estimate terms where at least one of the indices is large. Large in the sense bigger than L or bigger than M. And here we can then rely on the decay, on the exponential decay of the exponential term. So that is what we would like to do. So we estimate also the Fourier coefficients just by a constant, the sine functions also by a constant. There's not so much to do a part of that. And what then remains are then series terms which have these exponential parts here. So to speak, we have here harmonic series in, what does that mean? If we allow t to go down to 0, it doesn't mean anything. For t to 0, what I did here was not allowed. For t to 0, I have here just 1. I have a non-convergent series here. So I have to stay, for this argument, I have to stay a little bit away from 0. Can be just a femtosecond, but I have to stay away from 0. That's not very nice, but so I'm not able to prove an estimate for the whole time interval, but only for a portion of it starting at a positive time. Because here, for this simple estimate, I have to take advantage of the strong decay of the exponential term, which means that the factor has to be here less than 1, that I have a convergent harmonics series here. If I have this, so if I stay away from 0, so if my time is bigger than some d bar, then I can estimate all these in the usual fashion by the harmonics series here, and I get here the corresponding terms with this part here in. If we now look at this term here, this means, what does this mean? We go to the other side. In the end, we get an estimate of this type here. It's a little bit tedious, and I'm only doing that in the end you appreciate correspondingly more the finite element analysis. So we get an estimate of this type where we have these exponential factors here. And if one, now what I've done here, I just plugged in the relationship between the L and the discretization parameter h, so I get here an h term. So what I have here is I have here a part which exponentially decays in h. So I have a much stronger decay than h squared, h3, h to the 4, or whatsoever. I have even here an exponential decay in h. I have e to the minus 1 over h to some power here. So if h goes to 0, this goes to infinity, this goes to minus infinity, and corresponding to 0, but much stronger than any power. So if I accept this fact that I have to stay away from 0, I can neglect this part. This will not harm me in any polynomial order of convergence estimate. So the only thing which I still have to see is the corresponding convergence of the remaining terms, of the lower frequency terms. So I have to deal with a deviation between the Fourier coefficients, here with h, here without h, and the eigenvalues, here with h, here without h. So I get a mixed term in between. For the Fourier, for the eigenvalues we have seen already, there's an order of convergence like h squared. The other term does not harm it. And here we have to look at the deviation. Sorry, this was this, and this goes then over to this term here by this argument here. And then we have, additionally, we have to look at the deviation in the Fourier coefficients. So what is here the difference? There's not so much difference in the Fourier coefficients. It's an argument. Okay, it's only by word. So maybe we go back and have a look at it again, what the Fourier coefficients were. So here you see it in the discrete case. And here you see it in the continuous case. And you see the scaling factor is exactly the same. And the only thing what happens here the double integral is substituted by a double sum. So what we apply is just the trapezoidal rule for the approximation of the integral on the underlying grid, to go from this part to this part. And this is also a process to this part. And at the boundary, we always have, here we are. Because at the boundary, we always get the 0 values for new, the values which are, where are we? Here. For the indices equal to 1 and equal to L and M, which are not included here. So this is just a matter of quadrature, and this is also of h squared. So in this sense, we have now shown, and we have to put it a little bit in quotation marks, we have shown order h squared of convergence for the approach. So what we would like to see, we get back the same spatial order of convergence also in the time-dependent problem. But you see, there are all kinds of restrictions we had to make. We had to work with the explicit solution, and there was one more severe situation, namely we really worked with the fact that all the eigenvalues are positive. So we have excluded the situation of pure Neumann, pure zero flux boundary conditions. We really have to have that all components decay exponentially. Fortunately, if we now go to the finite element situation, I think this I have a little bit better on the other transparencies. If we go to the finite element situation, the situation becomes much nicer. Okay. The first thing is what we do is we would of course take advantage of what we did for the stationary case. And this is now put together in the notion of the Ritz projection. What is the Ritz projection? The Ritz projection is a mapping, as it will turn out, a linear mapping from the big space V to the discrete ansatz space for an underlying V elliptic bilinear form, and it fulfills this property. Let's first think of the situation that A is actually a scalar product. Then this says that the error is orthogonal to the ansatz space. So in the case where A is a scalar product, in the symmetric case, we are just doing the orthogonal projection with respect to A, the A scalar product, on the ansatz space VH. Now we do now we do it also in the non-symmetric situation. That means we are, so to speak, going from the Ritz. Also, this is called the Ritz projection. We're going from the Ritz procedure, from the minimization procedure, to the variational equality procedure. Or you could also see it in another way. This RHV from the finite dimensional space is a finite element solution. A finite element solution of the problem which the element V is a solution of. What is the variational equation? I have any V from the big space. Okay, I call this W, the test function now. How do I have to define my W such that this holds true? Yeah, it's a little bit of a tautology. Of course, I have to define it as this thing here. The V is fixed. This gives me a linear, continuous linear form. And now, okay, let's do finite elements. VA, and I call this already RH of V. How did we call the test function here? VH, meinethalben auch. VH. Exactly what we have written down here. You see, this is basically, I consider the V as a solution of a variational form, and for this I take the finite element approximation. And that means everything what we know about the finite element, so to speak, about the mapping from the right-hand side to the finite element solution holds also true for the Ritz function. Linearity, boundedness, and in particular, what is then called So first of all, we see this is well defined, it's linear, it is continuous, and it's also what is called quasi-optimal approximation. That is, the error can be estimated by m over alpha, m being the continuity constant, alpha being the v-ellipticity constant of the bilinear form, times the infimum of all the approximation errors of the finite dimensional space. Because, yeah, this is just so to speak, it's just the old estimate, so to speak, Sear's lemma. But we will not say too much about it because we have, I think we have formulated this as an exercise, so you can think about that again a little bit in more detail. So this we will now use. This now encodes all our old knowledge. And this we will use now. And this is the statement which we can prove. And that's a very nice proof because it's very similar to what we did up till now, but it's much easier to do. It's much more general. The norms are a little bit different. So what is the statement? The statement is if the right-hand side is sufficiently smooth, and also the solution is sufficiently smooth, what we actually will need, we will see in the process of deriving the theorem, then we can estimate, for each instance of time, we can estimate the error. So you see, we really estimate here for every instance of time. There's no restriction with a lower bound or something like that. There's one distinction now in the norms here. You remember we have shown our estimates for the energy norms. We don't get this here for the energy norm. We only get this stability for the L2 norm. But of course we also have finite order of convergence estimates for the L2 norm for the finite element approximation. Or Nietzsche duality argument. So what is the statement? It's very similar to the stability statement which we have seen for the continuous problem, namely this deviation can be by three terms. The one reflects the influence of the approximation of the initial data. So the U0H is the one which we use in the finite element, in the definition of the finite element method. And this one is the Ritz projection of the initial data. So that would, this influence of this term is stamped exponentially with e to the minus alpha t, alpha being the ellipticity constant, which in some sense means, as we have seen already, being the smallest positive eigenvalue. Of course, also here in this situation, we cannot deal with a pure Neumann situation because we have assumed the ellipticity of the form. In the Neumann situation, a pure Neumann situation, we would not have this because there we would still have the constant solutions and the zero eigenvalue. Okay, so this term is as in the stability. As you see, in particular, if you take the additional effort and compute this here, that means solve a stationary finite element problem, and take this as initial data, there's no influence of the initial data whatsoever. Then there's another term which says this error is as good as the error of the Ritz approximation. That is a little bit in the direction of Sear's lemma. Or that is, it basically says the time-dependent problem is as good as the time-independent problem. So here we now can go on with corresponding error estimates for the stationary problem to make an order of convergence estimate out of that. And now there's an additional term where this additional regularity is required. And you see what is required. U prime has to be a function which is we will later see it has to be a continuous functions with values in L2, with values in capital H. So what do we have here? We have here the same thing, now for the time derivative of the solution. But this error term is damped in the way we have seen the damping of the right-hand sides in the parabolic equations. Okay, let's prove this. Let's now compare it to all the other index mess around a very simple proof. So what do we do? This is the error, that is the term we would like to estimate. So we would like to take advantage of the Ritz projection, so we put it in here, the Ritz projection, and here again. So we have now two terms, this term theta of t and this term rho of t. And you see, theta of t is now a function which is VH valued, which is only in the finite, only takes values in the finite dimensional space. The UH is in the finite dimensional, and this is also. Here, this is of course not the case, because here the solution comes in. So now we just test. So we, why is this so? Okay, now we have to think about what is in this last line. And as I have nothing with me, we have to think what it is. So what do? We just plug in the test function VH. So we have here the time derivative, the A term, and now we bring in okay. Let's see what the next conclusion is. The next conclusion is this one here. So what do we have here? We have here this term with the UH prime. If we subtract, we get here the U prime, and now the other terms must fit. In the sense that, okay, the right-hand side goes away, the F term is gone. Theta, what is theta? Theta is UH minus RHU. So the statement is here. Here we have UH minus RHU. So the only thing what is so to speak changed, we have substituted okay. The only thing what we are going to use is basically this definition here. So that means everywhere where we have the solution and we test discretely, not with the full space, but only discretely, we can substitute the solution by the Ritz approximation. That's again the error orthogonality, which is basic for all the error estimates. So I think we do not need this line at all. We just look at the next one. So what was this? So by the subtractions, what was the theta? UH minus RHU. We have just subtracted the two equations. Right-hand side is gone. UH minus, then we have here also the UH term, and then from the subtraction we would get the U term, but the U term here in the A form we can substitute by the RH of U term, exactly by this defining property. Okay, so this means now we bring this together, then we have this term. We now write this in the, now we would write this as we have the theta already here, we would also have to have the time derivative of theta. So we have now this term and this term. So we have to bring this term is okay. This term is this term, and this is the correcting term, which so to speak adopts which takes again the RH away here and relates to this form here. So this is just now direct substitution by the definition. Okay, Now, what was the definition of the rho, or of the minus rho? The minus rho was u minus RH of u. Okay, what do we have? We have the u minus RH of u. And from this, the time derivative. So we have this term here. So in between, wait a second. At some place we have we should have done something which I should comment. Namely, we have exchanged the time derivative and RH. So we have used the identity that the time derivative of RH of u is the same as RH, the time derivative of u. And I think this we have done here in this in transforming to this equation. So this is also, I'm not sure whether this is also an exercise, but I write it down. What we have used is the following identity. I take u of t. Of course, u of t must be from v, that I can do that. And here I can RH of ut. That this makes some sense. Of course, I need something like u being a continuous function with values in v, something like that. That I really can write down u of t. So now I can, this is again a function in time. This function might have a time derivative or not. And the assertion is this has a time derivative if u has a time derivative, a classical time derivative. So this is what is meant by smooth enough. And I'm now not 100% sure whether we need here u or v, but let's go to the safe side and assume this. Then on the other hand, we could also look at this function. Yeah, I think we need this. So this also makes sense. Pointwise is also an element from v. Of course, we could also do this thing here, and the assertion is then there is identity. And why is this the case? Think of difference quotients here and here. Difference quotients, there's no problem because RH is a continuous, is a linear operator. But RH is also a continuous operator. That is, there's also an exchangeability of the limits. And that gives you this identity not only for the corresponding difference quotients, but also for the difference quotients. Of course, this really means the derivative is the limit of the difference quotients in these spaces. That means we really need in these spaces classical derivatives, not weak derivatives. That is what was hidden behind this notion sufficiently smooth. And this exchangeability we have used at this place here, because actually we would have here RH of u prime, which we have exchanged here. But if we are here already now, the rest is just the stability estimate for the continuous problem, which we have seen already, which of course also applies here the basic space we are using, that is, so to speak, now the space VH, because the theta is VH valued. And this tells us we can estimate pointwise in time the L2 value in terms of the corresponding initial value with the exponential decay term. The right-hand side, we need a norm of the right-hand side. So the L2 norm of rho prime is okay times a corresponding initial exponential term. So, okay, and now we just plug in. And here we can, what is theta? Here we have, sorry, wrong direction. What was the theta? Here we have the initial data and the Ritz projection of the initial data. This was the first term here, so we have seen this term here. The next thing is we see this term here. And this term here comes just in by triangle inequality. So we now have said something about theta, and now we need already this term here. And this we just keep in the estimate. So this is just rho, what is written down here. So these two terms come from the theta estimate, and this is just the rho term here. And this gives then finally this proof. Yeah, next time we will then combine that with the h order of convergence estimate we know already, which tell us at least at this level, without time discretization, nothing goes wrong. And then the next question is, what are appropriate time discretizations that we keep this spatial order of convergence in a stable manner in time?